My name is Geiger. I'm a reporter for Group 2. Here to talk to you about the Rankine cycle. So here's basically an overview. I'm going to talk to you about, I have the data reduction, my assumptions that I use to try and do some calculations, and then the calculations themselves. This is just a little reminder of what the Rankine cycle is. 4 basic components: pump, boiler, turbine, and condenser. So here starts the data reduction. There's going to be a lot of graphs. And this one basically just shows that the fuel input was constant, but on the other ones you'll notice windows on those too, and that indicates the steady state. So this is one of the indicators that we were in the steady state, is that we need to be around 110 psi. So that's here what the box is indicating. And also on this bottom, I set 0s when we actually started recording data instead of the time that it was actually, we've been running it for a while. So I just did it when steady state was pretty much achieved. This is another one of the things we look toward to know we're in steady state. The voltage needs to be about 6 volts. The generator amps need to be somewhere between 0.2 and 0.4. You can see that there's a lot of variation, and that's because it was controlled by 2 of us during the experiment. So I mean, you literally had to turn a knob, so that's why it's all kind of over the place. And so then on these next ones, the dots indicates the point that I chose to base my analysis on. This is the boiler temperature, the turbine inlet and outlet pressure, turbine temperature, generator RPM, and then this table pretty much is what you actually need to know. It summarizes all those parts. The terms in bold indicate the most important measurements in this experiment. And I just wanted to point something out that's kind of interesting. The boiler pressure was 110 psi, but then we had a significant drop to the inlet of the turbine, which seems awfully like a huge drop in pressure. So we must have had a lot of losses in between the exit of the boiler and entering the turbine. So these are some of the assumptions I made to try and make sense of the data. I said that when the water was entering the boiler, it was a saturated liquid. And then I said that when the water enters the turbine, it's a superheated vapor, which is kind of definition of Rankine cycle. And then as it leaves the condenser, it's supposed to be condensed back to a saturated liquid. I use these assumptions to then use the steam tables to find all of the relevant data at each state. Most importantly, the enthalpy at each state, because that's what we use to determine the work and the heat. So first I did the boiler. I used the difference between the entrance of the turbine minus the enthalpy at the entrance to the boiler, but that's mass specific. So then obviously we need to find the mass flow rate. The mass flow rate was found by using the water that we used in the boiler divided by the time of the experiment, which I found to be about 0.007 kilograms per second. The heat rate I then found out of the boiler was about 15.5 kilowatts, which seems high. And then the heat input by the liquid propane fuel tank was calculated to be about 22.9 kilowatts. I found that using the fuel rate, the fuel input rate, as well as I looked at the energy density of propane. And I found that the efficiency of the boiler was about 32%. So I next did the turbine or the generator, and I found that the work output of the turbine would to be approximately 930 watts. This was kind of tricky. I didn't know exactly how to find the enthalpy per se, because you can't assume that at state 4 it's a saturated liquid, because I mean it's not into a cycle, so it's not going to work perfectly. So I found this equation, and that's how I found enthalpy. This is the specific heat at a constant pressure for steam. I found the power that the generator is outputting to be about 2.02 watts. That's also on the data. And the efficiency seems to be 0.2%, which seems extremely low, so I'll probably mess something up here, which I did it and knew it was wrong, but then I didn't necessarily know how to fix it, so that's that. I next did the condenser, and that the heat out of the condenser was about 16.8 watts, and that the input, that the work of that the pump did of 2.2 kilowatts. So this cycle efficiency represents the real cycle, which I found to the output of heat over the input, which is about 8.27%, which is low, but it's a little bit higher than output. happen, but it's, like I said, I definitely made some calculation errors just because the data that we got was not exactly straightforward into what it was actually telling us. So I did the ideal efficiency, assuming like we didn't have any losses, and that was, the net work divided by the heat we had to add, and that was about 20.2%. So the real efficiency is significantly lower. But like I said, we had lots of pointing out the inlet pressure of the turbine, just leaving the boiler, that was a significant pressure drop. So we must have lost a lot of steam, a lot of water there. So that right there is probably one of the main reasons that the efficiency was so low. I also calculated that the generator was super inefficient, but like I said, take that with a grain of salt. That was kind of a difficult, I didn't really know what to do there. And human error, because that we were controlling the steady state of the experiment, there was definitely room for error. You could see in our data, there's a lot of variation. It was going up and down. We were instructed to just choose a point within the steady state to do our analysis. So it could have been maybe not the best point to choose. Maybe the results were a little bit weird, and maybe that's why some of my calculations were weird. I think for the experiments to work a little bit better, we need some more information about what the pressure and everything actually leaving the boiler is, and then as it actually enters the condenser. It's just kind of confusing based on what we had to know exactly how to apply the data that we did have. And as Mark says, then that's it. If there's any questions.